For the last century, urban engineering had one main goal during a storm: get the water off the streets as fast as physically possible. But in San Francisco, that speed creates a massive bottleneck. The city operates a combined sewer system. Rainwater rushing off the pavement pours down storm drains and mixes into the exact same underground pipes carrying raw household sewage. During a heavy downpour, those pipes hit capacity. To keep that mixture from backing up into people's homes, the system has to open relief valves and discharge partially treated wastewater, which is mostly stormwater, directly into the bay and the Pacific Ocean. Effectively managing urban flooding means intercepting that volume before it can push raw sewage into marine ecosystems. That stormwater also picks up an invisible chemical cocktail before it ever hits a drain. As cars drive, friction grinds microscopic pieces of rubber and brake dust directly into the asphalt. Researchers estimate that urban runoff transports 7 trillion microplastic particles into San Francisco Bay every year. Nearly half of those are black rubber fragments shed from tires, which carry a specific synthetic additive designed to protect the rubber from degrading. When that additive reacts with oxygen in the environment, it creates a chemical called 6-ppd quinone. It washes directly into streams, where it is highly toxic to aquatic life, particularly fish like the coho salmon. To intercept both the sheer volume of water and the toxic load it carries, San Francisco has set an ambitious target: manage 1 billion gallons of stormwater a year using patches of street-level vegetation rather than building larger concrete pipes. The question is how a few square feet of unassuming landscaping can filter 1 billion gallons of toxic runoff without relying on traditional gray engineering. A street corner rain garden is not typical landscaping. It is a highly engineered depression intentionally designed to flood. Looking at this cross-section of a bioretention installation, you can see the sequence. Runoff enters from the street and passes through a layer of mulch, followed by 18 inches of highly specified bioretention soil, before finally reaching the deep native dirt below. Instead of rushing into a pipe in seconds, the water is held in the soil's pore spaces. It percolates downward slowly, drastically delaying the time it takes to reach the bottom. Engineers call this a temporal buffer. Even if the garden eventually fills up and excess water overflows into the main sewer, that delay protects the underground pipes from being overwhelmed at the exact moment a storm is at its most intense. While the water sits in that soil, it undergoes an intense biological and chemical filtration process. Physical trapping happens first. Solid tire fragments and microplastics become physically wedged between grains of soil in the upper layers, preventing them from washing downstream. Below the surface, dissolved compounds bind directly to soil minerals. Meanwhile, the plant roots host complex microbial communities that actively consume and transform organic pollutants. This chart illustrates the results of those biological processes. Field tests show these gardens can trap up to 99% of incoming tire wear microplastics. And when we look at the concentration of toxic 6-ppd quinone entering the garden, the soil and roots reduce it by roughly 95% before it exits. Through this combination of chemistry and biology, these gardens function as decentralized ecological treatment plants. An isolated rain garden can only treat the water immediately around it, but when engineers hydraulically connect multiple gardens along a street, they begin to act as a unified system. By stringing these installations together across several blocks, planners can recreate the temporal buffering that a natural, undeveloped watershed used to provide. This map of San Francisco shows the city's ambition. Nearly 600 of these green infrastructure projects have been built or initiated, linking together across neighborhoods to collectively manage hundreds of millions of gallons of rainfall every year. This distributed network builds resilience into the city. If a single massive concrete pipe fails, an entire neighborhood floods. But a network of 600 independent gardens can absorb water, adapt locally, and compensate for heavy flows across the entire grid. Placing these billion-gallon systems involves layering multiple sets of urban data to maximize public benefit. The city overlaps data tracking heat vulnerability, low tree canopy, asthma, and flood exposure to pinpoint priority zones where needs intersect. A single project here manages stormwater while providing compounding benefits. Rain gardens cool the pavement, and native plants create habitat for pollinators. We don't need to tear up every road to fix urban hydrology. By inserting biology back into the pavement, a highly developed city can rebuild the ecological functions of a lost watershed without ever ceasing to be a dense, modern city.